So thanks a lot. I mean, thanks to Paolo for the nice introduction. It was great in Pisa. Okay, so what I'm going to talk about is a classical problem in quantitative finance, which is the problem of optimal execution by adopting some tools coming from reinforcement learning. So I'm going to introduce the problem in a general setting. Okay, so as you know, optimal execution is the way of optimally executing typically a large amount of trades. The problem is a complicated problem that typically is divided into different sub-problems. If the order is very large that you want to trade, you have to decide how to trade optimally, for example, in different days, if you are really a big fan. But typically, the most important part of the optimal execution problem is how to trade within a day or a period during the day. And so the typical approach that is used is the one of adopting taking the window over which you want to trade, divide into macroscopic intervals, and try to optimize the way to trade in each interval. Then this is called the strategic phase. And then there is a tactical phase, which instead tells you in practice how do you want to trade in each of these sub-intervals. Okay, for example, if you want to send a limit order or a market order, if you want to trade in one market or another market. So we are going to focus on what is called the strategic phase of the optimal execution problem. And the problem in general is the fact that, okay, you want to execute a certain amount of shares, let's say Q, you divide into pieces and you trade incrementally through time to avoid to pay too much in terms of market impact. As soon as you trade, the price starts to move because of market impact in a direction which is not good for you because you are buying, and therefore you're going to pay more the next one, and so on and so forth. So at the end, the amount of money that you will pay for getting your position will be larger than the amount of money of that you would have paid in the market. Or if you want, the market position of your trade at the beginning of the period. So the problem is how those of you who don't know about optimal execution, the problem is how to optimally divide this trading units in order to minimize your cost. So, of course, there are different ways in which you can define what the cost and what the optimal objective is. We are going to use this presentation one of the not the unique, but one of the standard metric to define what is good and what is bad. And essentially, I want to liquidate in this case Q0 stocks within 0t. I divide this interval 0t into n sub-interval. In each of these sub-interval, I will trade the number of shares that I'm going to call VT. And trading VT, I'm going to pay a price which is called S tilde. Okay, this is the average price that I pay. And then my cost, my objective function that I want to minimize is this difference, the difference between the value of the position at the beginning and the value that I would that actually I get. Okay, it's zero the initial price. So in order to formalize this problem, this is just a standard introduction to optimal execution. I need to model in some way how the price will be modified by my trade. Okay, this will be essentially a market impact model. And well, first of all, why we do it? Well, essentially because market impact is present. Okay, so that's one of the left is one of the very first figures I made many years ago. Well, 20 years ago, more than 20 years ago, measuring market impact of individual transactions. So on the x-axis, you have the amount of shares that you trade. On the y-axis, you have the concurrent price change. And these, of course, are averages across stocks and across many trades. And what you observe is that, of course, when you buy, the price tends to move up. When you sell, the price tends to move down. In theory, this function is a nonlinear function, but as you will see, we're going to make the linear function. The other important problem, if you don't know much about optimal execution, is the fact that even if you know the price of, let's say, the mean price of the market, when you trade, you're going to pay a different amount, right? For example, if you want to trade a small amount, then you're going to pay half of the spread. If you want to trade more, probably you're going to trade a larger quantity. So in a way, this is standard, let's say, optimal execution. There are two sources of cost that you need to take into account. One is the permanent impact, so how much your trading is going to affect the future price. And the other one is the temporary impact, which is instead how much you pay with respect to the simultaneous price in the market. And that's the standard, let's say, model that has been proposed 25 years ago by Almgren and Chris, where essentially the idea of the model is that the price evolves as an arithmetic random motion, as a random walk, with a drift that depends on our speed of trading. Okay, and so this will be the drift that we are going to consider. And the price that we are going to pay in each interval, is equal to the market price minus if you are selling another component, which is called the temporary. So the first part is affected the price dynamics. The second part instead affect the price that we're going to do. And then, okay, we have this kind of model. We put this into the formula for the implementation shortcut, and we can apply the method for the optimization. So that's very standard. Okay, this is really very, very old. But let's see what are the main assumptions which are behind this approach. Well, the first one is that we are not going to touch for the moment, is that the permanent impact is linear. And so it's a linear function of the volume. We see that it's not true, but nevertheless. Then we have the temporary impact is linear, which is not true in reality. And the permanent impact, of course, is permanent. And then there are two important assumptions, which are the ones we're going to challenge in this lecture. The first one is that the liquidity, or which means the coefficient K and alpha tilde that describe the permanent temporary impact, are constant in time. So that liquidity is fixed throughout the period. Okay, and so I'm going to show you this is not true in reality. And the other important point is that only one agent is optimal executing at a given time, which means that when I trade, okay, I can consider the rest of the market as a background of white noise, of random walk, and then this is what is going to happen. And as I'm going to show you, this is in reality is not always. So what I'm going to present in this talk is a contribution from two papers that I brought with the PhD student, which is called Andrea Macri. One, we're going to consider the problem of optimal execution with time varying liquidity, and the other one, the optimal execution when more agents are present. And the tool I'm going to use is the tool of reinforcement learning. So let me motivate, before moving into the reinforcement learning, the reason why these two assumptions are important. Well, the first one is this graph. Actually, this is from these two papers by other PhD students, where it's not easy, but we try to estimate from the data how this coefficient of permanent and temporary impact vary throughout the day, to see if really there is a variability in time. And so I don't tell you the detail, if you read the paper, if you're interested in how we did it, but this is from the stock with Microsoft in one day. For Microsoft, this is the temporary, the estimated temporary impact in time. You clearly see that it is fluctuating, there's some peaks, there's some intraday pattern, so obviously liquidity in terms of temporary impact coefficient is not constant throughout the day. And the other one is permanent impact, it's much harder to measure in some sense. And in this case, you also see that during the day, you have a lot of fluctuations. So you cannot assume, like Almgren and Chris, that permanent impact and temporary impact coefficient are constant, but actually they are varying with time. And the other, yes?
Time from start of day or from the trade?
Okay, these are trades. Yes. Yeah.
But what is zero?
The beginning of the day. This is one day. Yeah, this is one day. So this is this is one trading day. Okay. So the other motivation is this comes from another paper for another old PhD student, where actually we had information about optimal execution of many investors in the market from a very nice database, and this is the impact of one of these optimal execution as a function of the volume when there is only one agent which is trading, when there are two agents that are simultaneously trading, when there are more agents that are trading. So obviously, you see it's a logarithmic scale, right? You see that the impact that you pay, the cost that you pay, strongly depend on the fact whether you are alone in trading or if there are many different investors that are trading simultaneously. And the reason is that, as we prove in the paper, empirically, is that very often if you buy a given stock, very likely most people will also execute large orders to buy. I mean, there is a herding phenomenon in optimal execution that creates, of course, a shift in your impact. Okay, so what we're going to do is try to use now reinforcement learning for solving the problem of the distribution in the general term. So why do we use reinforcement learning? Well, because it's model-free, because you don't need to estimate time varying parameter from the data. It's able to go beyond analytical approximation for specific solution, which will be clear in a moment. And the con, of course, is that it's hard to incorporate the effect of our action on the environment. So you need to be, so if you want to run on real data, then it's complicated because you need to know how your action would have modified the price, and typically require large data set. So we're going to consider what I'm going to show you. I'm not going to show you any data anymore. Okay, I'm going to show you only simulation, just to show you how the method, our method works. Okay. So if you're interested in measuring optimal execution when liquidity is time varying, essentially what we want to consider is the problem that, of course, liquidity is a very important quantity for trading, but liquidity is dynamic, as we have seen, and it is latent in the sense that it's a quantity that you don't observe. It's more or less like volatility, right? I mean, you don't observe volatility, right? It's a latent but important quantity. Historical data are not always suitable for the task, and if you want to have analytical solution, you need to simplify a lot your models that might not be coherent with the data, while in reinforcement learning, you have the freedom of finding the optimal solution for your problem. So the tool we are going to use is a specific class of reinforcement learning methods, which are called double deep Q learning. So I'm going to spend hopefully 5-10 minutes, because I was told to do so, reminding you a little bit about reinforcement learning, if you are not too much familiar with it. So the idea is that we want to optimize in an environment where you don't have any a priori assumption on the dynamics and how the environment is affected by behavior. So a reinforcement learning algorithm is composed by a state space where the elements are the state of the environment. This can be continuous or discrete variable. An action space, what are the action of the agent, and a reward function that tells you what is your reward if you are in state S and you take action A. And the system is defined as a Markov process by an initial state distribution and a transition probability, which depends, of course, on the past state and depends on your action. And the goal, then you have a reward, okay, as I told you, and the goal is to maximize or minimize, whatever, the total discounted reward. Okay, you have some discount factor, and then you want to maximize your reward. So in practice, what you want to do is try to find a policy. A policy is a map from the state of the system into the possible action. In general, this can be a probabilistic mapping in the sense that for a given state, you can have a certain probability which action you want to take. We are going to consider deterministic strategy. And the value of an action is defined as the expected value of a policy, sorry, given the expected value if I use the policy of my accumulated reward if I start from state S. Okay. And in reality, what I want to do is to, in order to optimize this problem, is either to consider, well, fixed discount factor, of course, and then either you consider the value function and you try to optimize in the space of policy the one that optimizes the value function, or you consider what is called the state action value function, where you fix the initial state and the initial action, and then you try to maximize, to find function Q that maximize this expected value of the reward given this initial condition. The optimal value function, of course, is the policy that maximizes the value function, and the optimal state action value function is the policy that maximizes the Q function. Okay, and there is some theorem that under some condition tells you that there is an optimal policy. So just to give a review of the methods, I mean, depending on what you know and what you can do, essentially you can divide the method in model-based reinforcement learning and model-free reinforcement learning. If the transition probability is known and you have a finite number of states, then essentially you can rewrite your optimization problem as a system of equation of S cardinal FBR of S equation, and then you solve it. We will be more interested in reinforcement, in model-free reinforcement learning, where you have two approach. Either you parameterize the policies, so the policies will depend on a set of parameters, and you try to optimize the parameter that characterize the value of policies, or the alternative is that you try to optimize the value function, either B or Q. So essentially you parameterize the value function and not the policy. Okay, and this is what the direction where we are going to go. Okay, so if you have a finite number of states, then what you can do, what is called, if you're interested in optimizing the Q function, then you have what is called the Q learning. So if the number of states is finite, then essentially you can apply this iterative formula to find what is the optimal function. But this, of course, in some situation can be not optimal in the sense that, yes.
I'm just a learner of
why would you choose
the times are in your version.
right? Yes.
On the debate, they can be discrete and continuous.
Right. Here we're working in discrete time. So from the very beginning, I said the problem in discrete time, and this is the reason why we can use the TQL. Okay, that's the reason. And so the key point is that if I have a continuum of states, not a discrete, if I don't want to discretize, well, the idea is instead to approximate the Q function by a neural network, and so essentially try to learn the function Q as a neural network. So optimal execution reinforcement learning is not a new topic. It has been around for a while. It's a list of some papers that try to find optimal policy for optimal execution. In particular, our starting point is this paper by Sebastian de Mungal and collaborator, which actually used double deep Q learning on real data without permanent impact to show that the method can learn a strategy will outperform benchmark, like for example, the TWAP. The TWAP means you trade at constant. Okay, so the advantage of this approach is that you can run on real data. Of course, you have to assume that you don't have impact, because otherwise you don't know how to modify the real data by your action. And then they were able to prove empirically, essentially, that their method is able to outperform the TWAP. Okay, so what is our architecture for this? That actually is going to be used in both parts of the paper. Well, essentially, we have as usual the training and testing phase. We simulate ST from different scenarios of different market impact model. I mean, variation of the algorithm increase. I want to sell a certain number of shares Q0. I'm going to consider two different settings, which will be very important. In one setting, the state will be composed by the remaining inventory that I have at time t and the time t in the or the other possibility is that I take my state function, my state variable, the inventory, the time, and the past price. So I'm going to show that in some situation, adding the price as a state function improves significantly the performance of the reinforcement. Okay, you have a full liquidation over figure 0t. I'm going to use an exploration scheme, which means that I have an epsilon greedy policy, which means that the VP that I'm going to trade is with some probability is randomly chosen among the potential possible strategies, and in other situation is going to be taken as the one that maximizes the neural network. Okay, double deep Q learning, maybe I have a figure that might be useful. The double deep Q learning is a method that uses two neural networks. One network is called main, and the other one which is called target. Essentially, the point is that the first network is used to find what is the optimal volume that you want to trade. Okay. The other one is going to evaluate the performance of the first network by taking the reward of the target minus the value predicted by the link. And then the update of the weights of the two networks is done in an asynchronous way. And essentially what is going to happen is that from time to time, the weights, this is the copy of this network, and from time to time, the weights of this network are going to be copied into the target. Okay, and this is done in order to improve the stability and avoid oscillation of the gradient. It's a bit technical, so I'm not going to go too much into the detail. So let's look now at what we did. Okay, so essentially the idea is that in the testing phase, okay, we have trained our neural network. We calculate the average trading strategy and implementation shortfall, and then essentially we're going to compare the cache of our optimal strategy, the cache that we obtain with the cache, if this is available, of, for example, of the optimal of some benchmark strategy that we can obtain. Okay, so architecturally the system is composed by, okay, we have 10,000 training episodes, we have 5,000 test episodes. The two neural network contains identical, of course. They contain 5 layers, 20 hidden nodes, okay, Adam optimizer, and so on and so forth. So what are the scheme that we are going to consider? Well, the scheme are again the Algren increase. And okay, in the standard Algren increase, well, the problem is actually it's a quadratic problem. So, I mean, it is good that we obtain the correct result, but essentially it's not that surprising. Then what we need is to consider instead situation where the impact coefficients are varying with time. And in particular, we consider two different scenarios. In the first scenario, the permanent and temporary impact varies linearly with time. So either the impact increase or the impact decrease with the variation that I'm going to show you. If this is the case, then actually you can find the optimal solution analytically, and so you can compare whether the machine is able to learn the optimal strategy. And the last approach is the case where impact, so the parameter alpha and kappa, right, alpha tilde and kappa, are following some stochastic process. Okay, so just to give you an idea about the output of this, so this is the one typical output. So of course now our state is Q, P, and S. Okay, S is the normalized price, and so these are different slides for different value of the price. And here you have time, and here you have the inventory that you have, and for each value of inventory, time, and price, we get what is the optimal amount of shares to trade. For example, in this case, we have a decreasing impact. So you can imagine that a decreasing impact is optimal for you to trade more toward the end than the beginning, right? Because at the end, the stock is going to, the transaction is going to be cheaper. And in fact, in this case, the machine learns to trade more toward the end than less at the beginning. Okay, this is just to show you that you get reasonable result. While of course, if you have increasing, then you get a similar result. What is most interesting is the case when, okay, that's pretty trivial. But let's say now let's consider a situation where I trained my machine with both increasing and decreasing pattern. Okay, so the pattern that I give in the training phase contain both increasing and decreasing market impact coefficient. But then I test only in one of them. Okay, so I say I've trained in the universe, but then I want the machine to be able, while trading, to learn whether the testing scenario is a scenario where the impact is decreasing or increasing. Okay, and what is your benchmark? Well, if you know that 50% that the price is going to, the impact is going to increase or to decrease, well, your benchmark will be, of course, to trade at constant speed, as if the market impact will be constant. And what we found is indeed that if you use as state variable Q and T, then essentially the method is not going to outperform the QA, right? Why, if you use Q, P, and S, so if you use also the price as a state variable for your reinforcement learning method, then you get a significant outperformance with respect to the method. So what does it mean? It means that you train your system on scenarios where the liquidity can go up or liquidity can go down. Then you test on one of them. Okay, it doesn't matter which of the two. Okay, this is increasing, decreasing, right? You test in one of them and you show that the machine is able to detect through its own trading and the dynamic of the past price whether the impact is decreasing or increasing, and find a trading strategy which is better than the one that you would do agnostically by trading at a cost plus. Okay, so it learns in a really uncertain scenario. And a similar phenomenon can be observed with stochastic impact. So that's a more sophisticated time varying impact. So it's a model where essentially, okay, this is a continuous time version which is taken by this paper by Barger and Loring, that of course is discretized. So in this case, you have that the price follow an arithmetic Brownian motion with the drift and of permanent impact, but the permanent impact coefficient follows a shear process, essentially a stochastic process, mean reverting stochastic process, with mean revert to the value theta k. And similarly, the temporary impact coefficient follows another shear process with another parameter. And the noise, the two Brownian motion that drive the dynamics of the impact parameter might be even correct. Okay? So what this guy did is to solve this optimal execution problem under the assumption that the deviation of the impact parameter from the equilibrium value is small. Okay, small fluctuation of liquidity around the long-term value, theta k and theta alpha, and this is the optimal solution. Of course, you see that if theta k is equal to kappa and theta alpha, so if alpha is equal to theta alpha, and kappa is equal to theta k, then the optimal solution is the D1, the model speed. Okay, and this is the correction, it's a dynamical correction, of course, you need to do stochastic optimization here. Is the optimal correction that you need to do in your trading velocity in order to take into account what you have. Of course, the problem is there are two problems, right? The first problem is that in order to implement in practice this, well, first of all, you have to be in a scenario where liquidity varies a little, but impact varies a little around the equilibrium value. Second, in order to implement this strategy, you need to know to be able to estimate in real time this point. So what we want to see is whether under this scenario, a reinforcement learning approach is able to, well, overcome this fact. And the answer is yes. Okay, so actually this is the case where so the comparison here to the delta PNL, of course, is the delta PNL with respect to the solution, the analytical solution, approximate analytical solution. So we see that we don't need to estimate parameter. Of course, the machine is going to estimate parameter while learning. And essentially what you see is that the delta PNL, well, it is positive with respect to the benchmark, even when the fluctuations are small with respect to the equilibrium value, and when the fluctuations are large, well, the delta PNL is even larger, because of course the approximated solution by Barger and Loring is of course not appropriate. And so in this way you are able to
the inside, because in your figures when you like up down,
right.
You have when you didn't have price,
right,
you had a negative result.
Yes,
but
yes.
here
You still have a positive result, especially if this value seems to be very high. I agree with you. I don't have anything like that, but I agree with you that this is not obvious at all. I mean, it's not clear that so maybe it's not really price. So in the other case, it's the price which is important, because you want to know whether you are in a scenario where this is increasing. You are measuring the you are measuring the impact while trading in the previous case. Exactly. You are filtering it. So here I don't have anything here. Right. All right. So let me move to the second part. Okay. Let me skip this, which is the part where we have instead multi-agent that are trading. Okay. So the problem is here that now instead of having one agent, a reinforcement learning agent, which is optimal executing, you can have multiple agents which are simultaneously trading. And so the problem we want to know is what type of optimal execution strategy will be found by two or many. Now we will show two two reinforcement learners that simultaneously are trained to trade to optimally execute some order. I mean, this problem from a mathematical point of view actually is being tackled by many authors, because this can be casted as a market impact game. Okay, so what you do, you have two agents, and they want to optimally execute an order, so they don't have any more one agent optimization, but actually what you need to have is an equilibrium between the two. Okay, and this is typically obtained via Nash equilibrium. And so, okay, I can skip this. It's not important. So, in particular, we're going to consider a situation where actually we can solve the Nash. We can find the closed form Nash equilibrium for the market impact game. It's going to be under an increase at the end, and we are going to find whether the reinforcement learner are able to find the Nash equilibrium, or if they find some other structure. Okay. Then we are going to comment about what this is going to be.
One question.
Sure.
Any comment on time dependent impact?
Right.
And
going back to the previous one.
Yeah.
Yeah, this is time dependent impact. Because the impact parameter is fluctuating there, right?
Yeah, but I mean the time decay of the fact, because you have a trend.
Right.
But it would be
sure. Well, the decay, I mean, if it is not deterministic, the decay should be captured more or less by this story, right? Right. And so we wanted to, so we didn't try to do with stochastic process that mimic what we observed during the day. So we separately consider the case when the impact parameter can be increasing or decreasing, but linear.
The impact itself can be a decay function. Right? That's the reason I asked the question.
Oh, you mean when you feel like transient? Be like transient?
Yeah,
like transient.
I mean, transit, but long enough. So not
right.
10 years.
Yeah.
Slowly decay.
Good. That's very good. We are working on that. Of course, you can imagine, because I work a lot with transient impact. I mean, here we only use angular increase.
It's very interesting to find out if you're really able to think.
Right, exactly. That's a good point. I mean, we are trying to we are working on this. The machine is able to find the optimal solution for the transient impact model. This is clear. We are also interested in the market impact game with transient impact, because there is this paper, I don't know, it's paper by Shield showing that you can get instability in the price if impact is transient, but it's not clear whether it's able. So we don't have time varying transient impact model. So where the kernel is time. This is still not in the pipeline. But
the second question, risk.
Right. The risk. Oh, that's a very good question. We have risk neutral investment. Okay, totally risk neutral. We are thinking about how to do it. I'm not sure about. Sorry. Well, you mean like adding actually there are two possibilities. I do a quadratic penalty like with inventory, or your reward that should be related to a factor.
Because I know in the reinforcement learning it's actually quite difficult.
Yeah, I know. That's why we stick to risk neutral. No, but that's a point we are not working on that, but I know that this is a big issue. Okay. Right. So what is our, how much time do I have, Paolo? Okay. Let's say 10. I'm going to be done in 10 minutes. Okay. Maybe we'll see something. Okay. So the key point is that okay, now we have multiple agents. Each agent has to solve the same problem as before, but the dynamic of the price now is slightly different. Why? Because the temporary impact remains the same, right? I mean, how much I pay with respect to how much I'm agent paying. How much I pay with respect to the market depends only on my trade. However, the market impact depends on what I trade and what Nash I trade, right? The sum of the two. Okay, so that's where the coupling between the two is happening. And in this case, Shield and Zhang in 2017 found that in this case there is a unique Nash equilibrium that I'm going to show you for this problem. Okay, now the problem is whether reinforcement learning agents are able to identify this Nash equilibrium, or they find different equilibria. For example, there can be equilibria that can be thought as possible collusion, okay, that they find a different way of gaining both match or supra-competitive equilibrium. Okay, so I need to go a little bit fast. So following some paper by Ramacont, that did the same for market making. So essentially the idea is to define a collusion as a strategy such that the total implementation shortfall is going to be smaller or equal to the implementation shortfall in any iteration that this agent have, which at the end is quite similar to what is called a Pareto optimum. So it's a technical definition of a Pareto optimum that tells you essentially that there is a strategy that outperforms the other. And in fact, it is possible to find that for this game, collusive strategy and Pareto optimal strategy are essentially the same. One can find analytically the Pareto optimum strategy by solving the problem of minimizing the total implementation shortfall for both agents under the constraint that the agents are able to trade everything. And well, maybe not surprisingly, you find that the Pareto optimal strategy is that both agents trade as if they were alone. If they were alone, they would trade at a constant speed, right? And the Pareto optimal strategy is the strategy where both agents trade at the optimal, which is different from the Nash equilibrium. The Nash equilibrium, as I'm going to show you, is completely different. And actually, for this type of game, which is, you know, a two-agent under an increased market impact game, you can actually characterize the whole Pareto efficient set of solutions. I remind you that the Pareto frontier is a frontier such that the implementation shortfall of one agent cannot be decreased without increasing the implementation shortfall of the other agent. The Pareto front. And this can be found numerically by solving this multi-objective optimization, where you try to minimize simultaneously the implementation shortfall of both under this constraint. And for this problem, this can be easily solved numerically. So let me show you what we did. Okay, so the problem is what the reinforcement learners are going to learn. Are they going to learn the Nash equilibrium, the solution of the game, or are going to find the Pareto solution if they are allowed to trade? So what we do is that we model the two agents using, again, the same architecture. So I'm going to skip the architecture. So again, each agent will be a double deep Q learner. Okay, both agents are trained simultaneously in the same environment, and we want to understand which type of equilibrium defined when we test, of course, out of sample to see if there is some sort of supra-competitive or collusion-like strategy. So the setting is very similar to the previous one. Okay, I can skip this because it's exactly the same. So the only point I want to mention is that okay, we tested here different value of volatility, right? The volatility of the asset. We test 2,500 iteration. Okay, these are the parameters. So we will have essentially three scenarios. So very low volatility, essentially intermediate volatility and high volatility. And you know the impact parameter here are fixed. Okay, and this is what they want to learn. So what do they learn? Okay, that's the figure. Okay, I told you that we did 20 rounds of 2,500 iteration each. So we will have in the testing phase, right? So we have, I'm going to show you in the next block. For each testing run, we have 2,500 points. Okay, we take the centroid of these 2,500 points in the plane. In the plane, we have the implementation shortfall of agent 2 versus the implementation shortfall of agent 1. Okay, the star is the Nash equilibrium according to the theoretical value of Firenze. Okay, that can be computed. The black line that you see here is the Pareto frontier. Okay, so and the star here is the Pareto optimal implementation. So the implementation shortfall corresponds to the Pareto. Okay, so each of these points, so the different colors refer to different volatility values. Okay, each of these points is the centroid across these 2,500 in order to have a large setting of value. And what you see is that in most of the cases, the agent learn an equilibrium which is much closer to the Pareto rather than the Nash. I mean, now there is a debate whether you can call this collusion or supra-competitive subsets, But clearly, when these machines are allowed to trade simultaneously, they tend to find equilibrium that clearly the different problem. The one you would expect under game theory. Okay, that's the key point. And the result is quite robust. Okay, these are the strategy. Okay, this is the impact for the different volatility. Okay, this is the inventory as a function of time. So the Pareto, which is also the TWAP, so constant speed with the green line. Okay, the analytical, the Nash equilibrium is given by this. Okay, these are risk neutral agent. Okay, yes.
Only two machines.
Only two machines.
And we don't have a market. They will.
They do have.
I
mean, the drift are the two machines, right? The drift is given by the two machines. Right. Then, of course, you have some noise. Okay, the rest of the market is the noise. In fact, sigma here tells you how big is the rest of the market. But the rest of the market is random. Okay, that's it. Okay, so this is the agent are risk neutral, right? Nevertheless, what results show that the Nash equilibrium of this market impact game is the same that you very similar. The one that you would get if they were risk averse, right? In Algren increase risk averse a single agent, you have a front running. Of course, you trade more at the beginning and less toward the end because you want to minimize risk coming from trading at the end. Okay, so this is very similar. Okay, obviously these are the mean strategy, agent one and agent two, which obviously are different both from the Pareto and much closer to the Pareto, but different from the Pareto and from the Nash. Okay, so they learn a strategy which is somewhere different. This seems to be quite insensitive to the level of volatility, and in fact, it's also insensitive to the training and difference in training and testing conditions. So essentially, what we did to show the robustness of this is to train, for example, in the large noise environment. Volatility is time based, right? So maybe you train in the large volatility regime, and then you test in a small volatility regime, and essentially you find these are now you see all the 2,520 points, right? These are the centroids. Essentially, you see that almost all the centroids lies between the Nash and the Pareto. So even if you have a misspecification of the volatility, this is not important. Of course, if you do the opposite, right, which means that you train small noise, but you test with large noise, well, this means, of course, that now the point in each iteration will be scattered all around. Of course, the large volatility is going to affect a lot of the implementation of the agent. But if you consider the centroid, with one exception, they all lie centrally in the Nash. Okay, so even if you have a misspecification, they are, remember, they are trained, but then they are tested with a huge noise. But still, they learn to trade. They trade in this way. Okay, I think I can stop here. So essentially, what we did in this second part is to study. Well, we can call collusive strategy. This is a little bit debated. The paper is out. We have not submitted yet, so and we have undecided whether to use or not to use the collusive there, because apparently there is a debate about this. People prefer to call supra-competitive in the sense that we go beyond the Nash, but it's not collusion, because collusion would require some sort of punishment. So if you do a collusion and the side to act in a different way, then I punish him in some way. And of course, we don't have evidence for the moment. This punishment is there. We are trying to investigate this. So we found the Pareto optimal Pareto distribution set in this game, and we found the Pareto optimal strategy. The T1, but most interestingly, we developed the double diffusion learning algorithm to model the two-agent trading under variable conditions. And it seems that the super-competitive collusive strategy naturally emerged in a model with agnostic setting. These collusive strategies are robust even when model parameter vary, showing the rate of volatility. And the strategy adjusts on the free spin and on the interaction effect. So essentially, they learn that the other agent is present in some sense, and they try to use it. I mean, I didn't mention, of course, because I was a little bit fast, but in the state space of the two machine learners, of the two reinforcement learners, there is the time, there is the inventory of the same agent, and there is the price, the last price, right? Of course, each agent doesn't know what is the inventory of the other agent, okay? The inventory level of the other agent. Okay, so it's not that, otherwise probably the result would be. But in a realistic setting, of course, an agent learns about the intention of the other agent indirectly through the price. That is what that in finance. Okay, that's all. Sorry, I hope it's not too late. The paper are out if you're interested. And
Comes down to
yeah.